Okay, everybody. Last little shot at gases here is the last law. It's not really a law. It's just more of a. It's in a way, it's a common sense thing, but it gets a little twisty and along the way. And that's when we deal with mixtures of gases. When we do mixtures of gases, we have to keep a couple of things in mind. So we look at Dalton's law of partial pressures, and again, the word partial pressure should give you a little indication that we're going to treat each gas as if it has its own pressure. So when you put gases together, they're pretty much going to combine these pressures, but it can be a little tricky when with the data that they give you. So let's just look at the main idea here is that in each gas, if you have a mixture of gases, each gas is going to have its own pressure. Okay, but we have to understand one thing: the total pressure of a mixture of gases is equal to the sum of the partial pressures of each gas. So we're going to assume each gas has its own pressure. So then we add them all together, we're going to sum up those pressures into a total pressure in something. Okay, so that's how we can look at this. All right, so if you have one gas at 2 atm, another gas at 1 atm, another gas at 3 atm, and you put them together in a container of the same size, you would then add them together such that the total pressure, P total, is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3. So if you add 2 plus 1 plus 3 together, you get 6. Great. All right, so that's easy because they're giving us the pressures. So you just simply add the pressures together and you get that final pressure. Now, the only thing you have to worry about in this case, when you would do it this way, is that you have to be given the same units. So make sure if you to add all the pressures together, that you make sure that that you have all ATM or all KPA or all torr and such on. All right. Another way you can do this also, they can switch this around, is give you the total 6. I'll give you the pressure of gas number 1, which would be 2. Give you the gas pressure of number 2 would be, sorry, gas pressure of number 1 would be 2. Gas pressure of 2 would be 1. And then ask you what the pressure of the third one is. So they can give you the total and leave one of them out. And that, in this case, you'd have to subtract the total pressure from what's left and figure out X. So you can do that too. All right, so that's fine. However, what if they give you something a little different, like something called like this with when they give you moles instead? Now we know moles is not a pressure. So let's just say they give you a little balloon here. Let's say this little balloon here is sitting here, a little blue balloon, and it's got a mole of helium in it, and it's got 3 moles of xenon. All right, and the total pressure in this balloon is 800 millimeters of mercury. So we know that the pressure of the helium plus the pressure of the xenon would have to equal the total pressure in the balloon. However, we're not given pressures, we're given moles. Now, I want you to think about this a little bit. Think about the fact that moles is really the number of particles. So if you have a number of particles of helium that are pushing on the walls of the balloon, so you think about these guys bouncing off the wall of the balloon. So there's a mole of helium, but there's 3 times the particle amount of xenon. Okay? So really, together, there's 4 total moles. So 3 plus 1 is 4 total moles. So let's just keep that in mind that we have here. So you could really give an idea that most of the moles of helium is really going to be responsible for most of the pressure, right? So that's right, okay? And a very little bit is going to be from the response of the helium because there's less helium. So the question is going to ask you, say you give in moles, okay, you want to find something called a mole fraction first. And what the mole fraction simply is the part, it's actually percent composition in moles. So you have a total of 4 moles, okay? So the percent composition of moles of helium is really 1 divided by 4, right? So it's the whole thing, which would be 4, and it's 1 divided by 4 for helium. It would be 3 divided by 4 for xenon. All right, so the mole fraction is always the moles of a single gas divided by the total moles of gas. Very similar to the part over the whole, okay? I like thinking as part of a whole mole. So it's the moles over the whole moles, and that's called the mole fraction. So then what we'll do is we'll use that mole fraction, and we're going to multiply it by the total pressure in the balloon or in the tank, and that'll give you the partial pressure of the single gas in the mixture. All right, so it makes sense, right? Because if you think about it, right, 1 mole of helium is going to produce less pressure in the 800 than 3 moles would be. All right, so let's just figure this out. So what's the partial pressure in the above mixture? So we can say that the mole fraction, okay, so we can take is really the part over the whole mole. All right. So what we can do for helium, okay, we can say that 1 mole of helium over the total moles of 4, okay, and we can multiply that by 800 would be the pressure of helium, right? And then we can say for xenon, we can say 3/4 of the pressure is going to be for xenon. So if we do that, if we do those numbers quickly, we could say for 800, I mean, that's easy to do in your head, but we'll just do it anyway. 800 divided by 4 is going to be 200. Okay. We could say 200 millimeters of mercury. Now, of course, there's only 2 gases, so we could subtract 200 from 800 and get the rest of the xenon. But let's just see if we can double check it. And we'll take 0.7. We'll take 3 times 800, and then divide that by 4, which is really the same thing, which is again 600 millimeters of mercury. All right. So you can see, and together it makes 800, which is the total. All right. So just the helium would be producing 200, but the xenon would be producing 600 because 3 out of 4 moles. So it's kind of easy. It's an easy way to do that. So there's 2 ways they can ask you. They can ask you here by adding and subtracting pressures, or you can do it by moles. The only other way they can do that is not give you moles. They can give you grams and have you change to moles and then do this. So that's what we're going to do in the practice problem. So just take a look real quick. All right. So we get to the next thing, and we can do a couple little practice problems here. All right. So I'll put the 2 practice problems up. These are the 2 in your packet. Take a look real quick. So we'll go to yellow. Okay, and we have 64 grams of methane and we have 64 grams of oxygen are blown into a balloon. Okay, and we want to calculate the partial pressures of each gas in the balloon. Okay, and the total pressure is 100 torr. Now, again, they give you grams, and again, we have, grams aren't going to give you any pressure. We got to go to moles, right? So that's what we're going to have to do. So what we'll do is we'll draw a little balloon at the bottom, so we'll get an idea of what this looks like. So I'm going to do it first we're going to take care of the 64 grams of CH4. Okay, so we're going to change that to moles. We divide by the GFM, which is 16. Okay, we get 4 moles. All right. And then we will take, number 2, we'll take our 64 grams of oxygen. We'll divide by 32, which is your grams per mole. Okay. If not, you got to research on how to do that. All right. And then that will be 2 moles. So what am I looking like? In the balloon, I'm going to have 4 moles of CH4, and I'll have 2 moles of oxygen for a total of 6 moles. So I have 6 moles total. Okay. So for CH4, what's my partial pressure? If my partial pressure is going to be the mole fraction, I'm going to have 4 over 6, right? I'm going to have part over a whole. The part is 4, the whole is 6. And I'm going to times that by 1,000 torr. And you guess it, I get 667 torr. Okay. And for, that's oxygen here, O2. That's going to be the other part. So that would be 2/6 or a third times 1,000 is going to be 333 torr. Okay, so there's your partial pressure for methane, partial pressure of oxygen. And again, that's a pretty flammable balloon right there. All right. One other way you can do this, let's just say you have 4 moles of propane. So here's your balloon. Okay. We got 4 moles of propane. We have 3 moles of O2, and we have 1 mole of H2. Okay. We want to know the pressure of propane if the total pressure is 6.7. Again, they're only asking you about 1 gas here. Okay, again, you want the part over the whole mole. So the whole mole, the whole thing is you have 8 total moles, right? So we're interested in propane. We want to know the propane pressure. So propane is 4 out of the 8. So we're going to take 4 moles out of 8 total, right? And we're going to times that by 6.7 ATM, okay? And we should get a grand total of 3.35 ATM. So sometimes they'll ask you for all the gases, and sometimes they'll ask you for just some. Just make sure you're in the right units. Hope this helps. Very small little idea, but you get the idea. Okay. One other little application of this is a special case, and I wanted to share this with you because sometimes this comes up, and we want to be aware of it. Is that many times what scientists will try to do, and like what lab technicians will try to do, is produce a gas in a solution from water and make gases. Like they want to produce gases, and the problem is when they do it over water is this: when collecting gas from the space above a reaction, okay, done in water, one must account for the water vapor, which is always present. So again, whenever you try to collect things, water vapor will always be there. Okay, so if you want to find the pressure of just the gas you're collecting, you must subtract the pressure due to water. Okay, but the problem is the pressure of the water that's in there is going to depend on the temperature of the water solution. So it's a little complicated. So it's not hard. It's just you have to pay attention to it. So here's a scenario. You are collecting gas and you're bubbling it in here. You're making a gas and you're collecting it by almost like we did the mole rockets. And what you're doing is you're producing, here's the gas you want in here. And what that's going to do is that's going to produce the gas that you want. So you're going to start pushing the water out as it goes. Now, eventually, you're going to have space contains water vapor and gas equal to the ATM pressure. Now, once you stabilize the liquids here, again, once you make this even with the level of this liquid, that means ATM pressure is pushing here, right? That means the atmosphere pressure pushing here is the same as the pressure pushing in the flask. So these gases, these are equal now. Okay, so the liquid levels are balanced to equalize the pressure inside and outside the flask. Again, the pressure would be greater here if it was pushing this way, but when you finally collect all your gas in here, okay, now, not only do you have particles of your gas you want to collect, but you're also going to have, all right, you're also going to have in here gas particles of water that are influencing you because there's a water solution here, and you're going to have evaporating water. So that's going to actually be in here. So the total pressure in here is really equal to the gas that you want to collect plus whatever water vapor there is. So if you want to find just the gas that you want, you have to subtract all of these red particles, all right, which is what the question will give you. So none of these are, it's hard to do. It's just really a concept. So what you got to remember is the pressure total is equal to the gas that you're interested in plus whatever water vapor, right? So the pressure of the gas you're interested in is whatever the total pressure is in here, and you have to subtract the water vapor. So that's fine. And what the question will do is the question will give you the total pressure and the water vapor, so you just have to subtract them. Okay, so it can be very wordy, so that's what you have to be careful of. So what's the partial pressure of some nitrogen gas that's collected over water at 18 Celsius? Okay, so someone collected some nitrogen gas over 18 Celsius. The total pressure of the mixture is 740, and the vapor pressure of water is 15.5 kPa. All right, so that's what we want to do. So we know, number one, that the P total, okay, is equal to pressure of the N2, all right, plus the pressure of the H2O, which is what you don't want. You want to get rid of that. Okay, so the pressure total they're giving you is the 740. Okay, so they're giving you 740 millimeters of mercury. Okay, and that's going to equal the total of the pressure of nitrogen, PN2, which you don't know, plus the pressure of water, which is 15.5, right? It's 5.5 kPa. All right? So really all you have to do is subtract this from both sides. Okay, so the pressure of your N2 now is going to equal the total pressure of 740 minus 15.5, which is going to equal 724.5 kPa. Okay, so again, very easy, not a big deal. All right. Again, what's the concept? The concept is whenever you collect something over water and you collect it in a water solution, you're going to have water vapor that's mixed in with the gas you want to collect. So if you want to find that gas you want to collect, its pressure, you have to subtract the pressure for water vapor. That's all. All right. So I hope this helps. Again, do your problems. Make sure you're studying everything. Make sure you do the problems in the packet, and we'll talk to you soon.